And let's try to all be cheerful about it. All right, we started off with a question that was based entirely upon the lab that you just did. In fact, very many of the questions on there were based on the laboratory concepts. Here we have the decomposition of sodium hydrogen carbonate to get sodium carbonate, CO2, and water. This question simply says that we start with 0.08 moles of sodium hydrogen carbonate. How many moles of this stuff will you get? Now, when I wrote this, I thought that this was a really, really simple stoichiometry problem that you should have been familiar with. If we started with 2 moles of bicarbonate, we would obviously get 1 mole of carbonate, correct? That's simply the coefficients. So if we start with 0.08, we should get half as many moles. It's a simple 2 to 1. And so there should have been 0.04. Now, if you have a question on any of these as we go by, please say something, okay? And we'll try our best to work through anything you don't get. The next one. In the lab, you actually weighed out, about 3 grams or so. And you did the calculation to convert that to moles. Now, we all know how you convert mass to moles. Mass divided by molar mass is moles. Now, in this problem, you were given a mass and a molar mass, and really all you have to do is a simple division. 3.12 grams divided by 84 grams per mole. Grams would cancel, and you would get 0.0371 moles. If our yield of carbonate was 1.6 grams, how many moles of carbonate would that represent? Now again, this is the calculation that you did in lab. Remember, you calculated, you weighed the difference in your beakers, and the beaker was a certain number of grams of sodium carbonate. Just like the previous one, what we want to do here is take mass divided by molar mass and get moles. Our mass here is 1.67. Our molar mass is 105. Simply do our division, and this gives you 0.0158 moles of sodium carbonate. Once again, simply mass divided by molar mass. Please chime in if you don't get any of this, okay? All right, here, we're starting with a certain number of moles of sodium carbonate. That's what you calculated in lab, right? How many moles you started with, bicarbonate. You also calculated how many moles of product you got. What we want to do here is simply calculate the percent yield. That makes sense? All right. Our decomposition reaction looks like this. 2 bicarbonates, 1 carbonate, CO2, and water. Okay? So if we started with 0.25 moles of sodium hydrogen carbonate, how many moles of this stuff should we get? Our theoretical yield is what? Well, again, if we started with 2 moles, we would get 1, wouldn't we? So if we start with 0.025, we should get 0.0, well, we'll get half of this. So to calculate our yield, this is our actual yield here. That's our 0.11 moles, 0.011, right? That's the actual yield. Our theoretical yield is going to be half of this value, which is 0.0125. To calculate a yield, you simply take the ratio, multiply it by 100, and this is 88%. That makes sense? The only real thing that you have to remember to do in this is the fact that you're only going to get half as many moles here, because it takes 2 to make 1. If you start off with 0.025, you expect half as many moles of sodium carbonate. It takes 2 to make 1. All right, now we're going to take our yield here. We didn't do this in lab, so I just kind of made this up. But our yield was 0.11 moles. And we're going to dissolve it in water. We're going to dissolve it in 250 milliliters of water. And all we have to do is calculate the concentration. Now remember, when we calculate concentration, we're simply going to take our number of moles and divide it by our volume in liters. That gives us moles per liter or molarity. We are given that we have 0.11 moles and that we have 0.25 liters. Simply divide them, and this is 0.44 molar.
I guess this one, I would think that this is volume and moles at the top.
Because concentration is
Liters would be volume, correct?
Right.
So the confusion would be with having grams and moles.
Well, this isn't grams though. I mean, I gave you moles here.
So,
If I'd given you grams, you would have to do mass over molar mass to get moles.
yeah, that's the confusion, which we gave to which one. It said moles would be at the bottom in that formula. Moles over mass.
But here, you just have to remember, the units of molarity are simply moles divided by liters.
Yes, you have to remember that concentration is molarity.
Concentration is molarity,
And then if you know
and molarity is moles divided by liters.
But I think that's why some people didn't know when they heard the concentration word, what is it exactly?
Now, whenever we use the word concentration,
It's molarity.
at least in 110, we're talking molarity. Now, in 140, once again, you will address molality, you will address percentage, you will address parts per million, etc. But that's there, not here. All right, here we have a solution of sodium carbonate, and I'm telling you that this is 1.47 molar. That's 1.47 moles per liter. The question is, if we have 31.1 milliliters, or 0.031 1 liters. What will we have? And we're looking at moles here, okay? Now, there are 2 things that I told you to please always remember. Mass over molar mass was moles, right? And the other thing is concentration times volume is moles. Here we have a concentration and we have a volume. If we multiply concentration, that's moles per liter, by liters, we will get moles. So, our concentration here is 1.47 moles per liter. Our volume is 0.0311 liters. We simply multiply these and we get, what is it? 0.0457 moles of sodium carbonate. All right, everyone see that? That's just concentration times volume. Now, let's don't finish with this because this also has these other possible answers here. So let's look at B and C. If we have 0.0457 moles of sodium carbonate, how many moles of carbonate ion will we have in solution? Every sodium carbonate, remember the little flash thingy where the ions separate and bounce around in solution, okay? For every sodium carbonate, we will have 1 carbonate bouncing around. Well, that means that carbonate has to have the same concentration as the whole of sodium carbonate. Because 1 sodium carbonate is 1 carbonate. So we can say that B is not correct. This should be the same number, not half. All right, C. For every sodium carbonate that you dissolve, we're going to get 2 sodiums. So if sodium carbonate as a whole is 0.0457, we're going to have twice as many sodiums as we did sodium carbonates. Therefore, this is also correct. Twice that, twice this, gives us the molarity of sodium ions.
But in this question, if you just look at the question, you're not going to think that there's a coefficient of 2 in front of the sodium.
Well, that's why it's written out. So, A and C are both correct, which means that the correct answer here would be D. B is not correct. Once again, every sodium carbonate, if we had 1 mole of sodium carbonate, we would get 1 mole of carbonate. If we have 1 mole of sodium carbonate, we have 2 moles of sodium. So the concentration has to double for this and be the same for this. Think about the little flash thingy. They separate, they bounce around. Now this is being recorded. So if you want to listen to this again, if you have the stomach, you're certainly welcome to do it, okay? All right. This one was the only one that I think really was a touch complicated. All right, what we have here is we have 0.54 liters of solution. And we're going to add water to that. Okay? And we want to add enough water to that to make it 0.32 molar. Now, the total number of moles is not changing here, is it? We're just adding water. So we said what we do in a case like this is we're going to do concentration times volume for our initial and concentration times volume for our final. Because moles doesn't change, the initial moles and the final moles must be the same. Now we simply take and plug this in. Concentration and volume, that's these guys. Concentration, that's this one, and we don't know what the volume is. But we know they have to be the same. They must equal each other because the total number of moles hasn't changed. Let's take this, and we're going to solve for B2. So we're going to multiply these, divide by 0.32. When we do that, we get 1.32 liters as our final volume. All right, so you did all those calculations. That's good. You look at your answers. You see 1.32 up there. You feel good. But this is the tricky part of the problem, and maybe I should apologize for making it tricky. But remember, we're starting with half a liter here. This is our final volume, isn't it? So, because we're starting with 0.54, and we wind up with 1.32, how much water do we add? Well, that's just the difference. So we subtract those two, and we're going to add 776 milliliters, or 0.776 liters. As I was grading this, if somebody had even done 1.32, I would have been pleased. Okay? Again, the trick here is, and it was a little bit of a trick question, I apologize, but this is your final volume, B2. You're starting here, you have to go up to here, so you add this much water. All right, number 8. Here we have a simple limiting reactant problem, don't we? We have A, B, and C giving D and E. We have 2 moles of A. We have 2 moles of B, and we have 6 moles of C. No, we are given that we have 2 moles, and 6 moles. Okay? That's the problem. We're trying to identify the limiting reactant and see if this is correct. All right, we have 2 moles of A. How many moles do we need to do this reaction? Well, we only need 1, don't we? So we have plenty of A, don't we?
That's what. confused me.
we
I
have
thought
2
it was-
moles of B, which is what we need, 2 moles of B. We have 6 moles of C, which is what we need. So that means that we have lots of A, don't we? We have just enough B, just enough C. Don't we have lots of A? Therefore, A is not the limiting reactant, is it? In fact, B and C will both be limiting because we have just enough of those. All right, now let's say that we have our excess A reacting with 2 B's and 6 C's. How many D's will we make? This is in excess, so we have all we need. We have 2, we have 6, we're going to get 4, aren't we? Therefore, this is also correct. Then again, you look here and you see A and C. Obviously not A, B, and C because A cannot be limiting. Therefore, D is the best answer. We have all of the A we need. We have 2 moles. We only need 1. We have just enough B, just enough C to make 4 Ds.
I got confused because over there was 2 moles and then I didn't see 2 in there.
We have 2 A's,
Yeah.
2 B's, 6 C's.
And then I don't see the 2 before A, and I thought that you know, did not print or something. You know what I mean? Because over there, yeah.
All right, now this is one I put on here because I was trying to be a nice guy. We have 1 mole of sodium hydroxide, right? We're going to plop this in 10 liters of water. How many moles of sodium hydroxide are in there? Well, think about it this way. If you took a nickel and put it in a 10-liter bucket of water, how many nickels would be in there? 1. Okay. If you put a mole and you put it in 10 liters, how many moles are in there? 1. All right, I told you we were going to do pH increase and decrease. I know for a fact, again, that on the nursing board there are questions that are exactly like this. Because it's very important that in healthcare you do evaluate blood gases, you evaluate things like pH. And you need to know if somebody is becoming acidic or alkaline, right? You need to know that. Our pH is decreasing from 7 to 5. If the pH goes down, what happens to hydronium? It goes up. Remember, if the pH is lower than 7, it's acidic. If it's over 7, it's basic. So here we're becoming more acidic. So we're down to these 2. Are we going to increase by a factor of 2? Well, it's 2 pH units. But remember, every pH unit is a factor of 10. So it's 10 squared or 100. If the pH goes up, hydronium decreases. If the pH goes down, hydronium increases.
It's always opposite. When decrease,
This is 10 to the minus 7. This is 10 to the minus 5. 10 to the minus 5 is bigger, isn't it? It's bigger by 100 times. All right. This is a different equation because I got tired of the other one. We're simply taking sodium nitrate. We are warming it up, oxygen is evolved, and we're making sodium nitrite. It takes 2 moles of nitrate to make 2 moles of nitrite and 1 mole of oxygen. So we have, this should be a 3. Okay, I made a mistake there on the slide. But this is 0.4750 moles of this stuff, react. How many moles of oxygen will we get? Well, for every 2 moles, we get 1 mole, don't we? So if we had 2 moles of this, we would get 1 mole of oxygen. 2 moles of nitrate, again, I made a mistake here, that should be nitrate, give 1 mole of oxygen. Therefore, we need half as many moles. Take this, divide it by 2, 0.2375. It takes 2 to make 1. All right, we want to make a sodium carbonate solution. We want it to be 1.41 molar, right? We want 23 milliliters of it, or 0.023 liters. So, when we see something like this, all we're looking for is the number of moles here. We know that our concentration is going to be moles per liter. And we know that concentration times volume is always going to give us moles. All right, here we have a concentration, here we have a volume. That will tell us how many moles, won't it? Another way to think about it, just remember, moles divided by liters is molarity. Now here, we know molarity, we know volume in liters. Only thing we don't know is our moles. Concentration times volume will give us our moles. If you can't remember that, just remember our simple definition here. Moles divided by liters is molarity. We do this calculation, and we have 0.0324 moles. Concentration times volume is moles. Not to seem like I'm asking the same question over again. But we have a volume here, we have a concentration. How many moles are there?
Just have to convert the
Milliliters to liters. And then remember, concentration times our volume in liters is moles. Here's our concentration. Here's our volume in liters. Liter and per liter will cancel, just left with moles. And this is 0.18 moles, or 1.8 moles. concentration times volume. Yeah.
This one would kind of be confusing because it's not saying to round up. So you know, the answer is just going to be.
It was 175 or something like that?
1.771.
1.771.
Like I would be looking for.
Well, we're looking for two significant figures. So it would,
Closest one.
would have to round that up to two significant figures. On an exam, if you have a question like that, about rounding up or whatever, ask me, okay? All right, if we are given a hydronium, how do we calculate hydroxide? This is one of the things that should have been on your 3x5 card. As I see you looking at your 3x5 card, that's good. And you should save all your 3x5 cards. On the final, you're allowed to bring all 4 of them, okay? We remember that hydronium times hydroxide is always at 25 degrees, 1 times 10 to the minus 14. Okay? Hydronium times hydroxide is always 1 times 10 to the minus 14. So if we know hydronium, and we know 10 to the minus 14, we calculate hydroxide simply by taking this and dividing by this. When we do this calculation, hydroxide is 2.22 times 10 to the minus 5. The basic thing you have to remember is hydronium times hydroxide is 10 to the minus 14. That's always true. All right, which describes a basic solution? If the pH is less than 7, is it acidic or basic?
Acid.
It's acidic, right. Hydronium times hydroxide is less than 10 to the minus 14? Never. I mean, that's just stupid. Hydroxide is greater than hydronium. If you have more hydroxide in the solution than you do hydronium, it must be basic, right? So A, that would be acidic. B, this would be stupid. And C, if you have more hydroxide than hydronium, it must be basic. All right, here we have an acid-base reaction. We're looking for the conjugate acid and the conjugate base, and we're looking at the forward reaction. Okay? Now, what's happening here in our forward reaction? Hydrogen sulfate is being converted to sulfate, isn't it? Hydrogen carbonate is being converted to carbonic acid. So on this side, who is the Bronsted acid? Who's donating the proton? Who's donating the proton? This guy, right. This is the acid. This is the Bronsted base. All right, so step one, we've identified our Bronsted acid here. When you're looking for a conjugate acid-base pair, you start with the Bronsted acid, And then you simply ask the question, well, okay, this was the first question. What donates the proton? This stuff. Second question. After it donates the proton, it forms its conjugate base. So step one, you identify the Bronsted acid. Step two, you say, once it donates it, what does it form? And it forms sulfate. So the the conjugate acid-base pair that's correct here has to start with this and end with this. Step one, what's the acid? Step two, what's formed after it donates its proton? Oh, we're back to sodium carbonate again, huh? Now everybody should just turn their calculator off for this one, right? We're looking for how many moles of carbon dioxide we're going to get. If we have 84 grams of bicarbonate. Well, how much does 1 mole of bicarbonate weigh? 84 grams. Right? So we have 1 mole of it. You could do the thing about mass divided by molar mass. That's 1. You can do that in your head. So we have 1 mole of this, right? If we have 1 mole of this, how many moles of this are we going to get? It takes 2 to make 1. So we get half a mole of sodium carbonate, half a mole of CO2. Takes 2 to make 1. All right, what is true about conjugate acid-base pairs? The base will have 1 less proton and 1 less positive charge. How do you make the conjugate base? You take the acid and you allow it to donate its proton. When it does, the proton goes as a positive thing, doesn't it? So that means that the base must have 1 hydrogen less and 1 positive charge less. Now let's look at the rest of them. Conjugate acid will have 1 more proton? No, it doesn't accept a proton, it gives it up, doesn't it? Conjugate base is formed by reaction with hydronium. No. First of all, that doesn't make sense. But a conjugate acid-base pair is simply the Bronsted acid and what's formed after it gives up its proton. This is wrong, this is wrong. And of course, E is wrong. All right, this is straight off the tutorial. Again, I just opened the tutorial, took a number, and wrote them down. We have a pH of 12.26. We want POH, hydronium, and hydroxide. On your little card, you should have written these things. POH is 14 minus pH. Or pH plus POH is always 14. She also should have written 10 to the minus pH is hydronium. And 10 to the minus POH is hydroxide. So let's just take and do these. Here we have 14 minus 12.26 We're 1.74. Now here, again, I tried to tell everybody over and over again, please make friends with your calculator because they're all different. Don't practice these things. Here we would type in pH, change its sign, and hit 10 to the x. 10 to the minus 12.26, 5.5 times 10 to the minus 13. Same operation here. We know what POH is because we calculated it. So it's simply 10 to the minus 1.74 or 1.8 times 10 to the minus 2. Well, this was a simple neutralization, wasn't it? Lots of words here, but we have concentration and a volume. That gives us moles of KOH, right? We have a volume of acid, and we want to calculate the concentration. Concentration times volume, concentration times volume. Concentration of KOH is 0.25. The volume is 35 mils. We'll convert that to liters. Over here we have 10 mils, that's 0.01 liters, and we don't know the concentration of the acid. We simply multiply these, divide by 0.01, and our concentration, 0.875 moles per liter. And once again, on the extra credit, here I was trying to be nice, and so I gave you this. We have 10 mils of 0.02 molar acid. We're adding that to 10 mils of 0.02 molar base. What is our final hydronium ion concentration? Well, again, you can do this in your head, sort of. 0.01 liters, 0.02 molar, 0.01 liters, 0.02 molar. They're the same, aren't they? They're the same. So when we mix these two together, what are we going to have? It's going to be neutral. We're going to have sodium bromide. Remember, an acid and a base make a salt, and water. So, what's the pH of neutral water? 7. You just made water, didn't you? In your 10-liter bucket with the nickel in it. Hydronium ion is 10 to the minus 7 molar.